So let's do one more example here of an exponential model. All right, in this case, we have 2 hours after bacteria were introduced into a culture. The population was 256. 4 hours after the introduction, the population was 384. What will the population be 24 hours after the start of the experiment, assuming that the population follows an exponential growth model? All right, so in order to answer this question, we need to find the population after 24 hours. We first have to come up with a model that represents our population. We want the population as a function of time. All right, to find the population at t equals 24, we must first generate the population model. And because this is exponential growth, we know that our model is going to come in the form of y equals ae to the bx. Now, I'm going to change up the variables a little bit here. Instead of our independent variable being x, I'm going to make our independent variable t to represent time, right? This is a function of time. And instead of y, I'm going to rewrite that as p of t, p, capital P, representing the population. All right, so we now have p of t is equal to ae to the b times t. In order to complete this model, we must solve for the constants a and the constant b. And in order to do that, we have to think about how we can use the given information. All right, what are we told? Well, let's look at this first sentence here. 2 hours after bacteria were introduced into a culture, the population was 256. This means if I plug in 2 for time, I have to get out 256. In other words, P of 2 is equal to 256. And similarly, the second sentence of our question here says 4 hours after the introduction, the population was 384. This means that if I plug in 4 for time, I have to get out 384 bacteria. So I have these two pieces of information. All right, plugging these in to our model gives us AE raised to the B times 2 is equal to 256, and AE raised to the B times 4 is equal to 384. And so notice neither one of those gave us our constant A or our constant B. However, let's take a look. We have two unknowns, right? We have A and B, and we have two equations. All right, two separate unknowns, two separate equations. When we have two equations and two unknowns, we can solve this system of equations by using substitution. All right, we can isolate one of the unknowns in one equation and substitute that into our other equation. So let's start with this first equation here, and let's isolate A. Okay, we can isolate A by dividing by e to the 2b. This gives us A is equal to 256 divided by e raised to the 2b. Now, again, isolate the unknown value that's going to be easiest. Is it going to be easiest to isolate A or B? Definitely easier to isolate A. We just have to do some simple division. All right, so A is equal to 256 divided by e to the 2b. I can now substitute that quantity in for A into my second equation. Plugging that value in for A into the second equation gives me 256 divided by e to the 2b times e to the 4b has to equal 348. And now we just need to do some algebra that is going to simplify this expression. Notice, I have exponential quantities with like bases here. I have an e to the 4b, which will end up in the numerator, divided by an e to the 2b, which will end up in the denominator. When we divide exponential quantities with like bases, we subtract the exponents. 4b minus 2b leaves me with e to the 2b. So I have 256 e to the 2b is equal to 384. And that has given me an exponential equation. To solve this exponential equation, we begin by isolating this exponential quantity, e raised to the 2b. By dividing by 256, e raised to the 2b is equal to 1.5, and now I can take the natural log of both sides of the equation. The natural log of e to the 2b is equal to the natural log of 1.5. These inverse operations here give me 2b on the left-hand side of my equation, giving me finally b is equal to the natural log of 1.5 divided by 2. So now that we know what b is, we can solve for a by back substituting into this equation here where we isolated a. A is equal to 256 divided by e to the 2b. And again, we are going to plug in for b. This gives us a is equal to 256 e to the natural log of 1.5. Notice that when I multiply b by 2, the 2's are going to cancel out, right? This is 2 times b. 2 times b is just ln 1.5. And e to the ln 1.5, well, those are inverse operations of each other. They cancel out as well. This just gives us 256 divided by 1.5, which tells us that a is equal to 512 over 3. Okay, so go ahead, you can plug that into your calculator. You might notice you get a nasty, nasty fraction. Well, maybe not terribly nasty, or nasty decimal, but you can, not a nasty fraction, this is a nice fraction. You get a nasty decimal, but using the math frac feature of your calculator, we'll spit that out as a nice fraction, 512 over 3. Okay, so now that we have our constant b and our constant a, we can plug those back into our formula to get our model. All right, our model is p of t is equal to 512 over 3 e to the natural log of 1.5 over 2 times t. Again, that's a e to the b times t. All right, and now all we have to do is plug in 24 for t to find our population. One thing that might make this a little bit easier is to do some more algebraic manipulations to change this equation and make it look a little bit neater. All right, notice instead of dividing ln 1.5 by 2, I can divide t by 2. This gives us 512 e to the natural log of 1.5 times t over 2. Here I have multiplication of exponents. That is the equivalent of an exponent being raised to an exponent. And the reason we like this is because we now have e to the ln of 1.5, which just simplifies into 1.5 or 3 over 2, giving us our equation for p of t is equal to 512 over 3 times 3 over 2 raised to the t divided by 2. Okay, is this step absolutely necessary? I would say no. You could come up with your model and leave your final answer like this. I would accept that, right? But this does look much nicer and is going to make plugging in 24 much easier. So now we need to answer the question. What will the population be 24 hours after the start of the experiment? That means we are just plugging in 24 for t, plugging in 24 for t, and simplifying out gives us approximately 22,143 bacteria.